I think there are going to be a few more people, but I think we should get started. So it's my great pleasure to introduce Ramesh Budhani, who is coming from Wright-Patterson Air Force Laboratory. He's working there under the auspices of the U.S. National Academy of Sciences, National Research Council. So Ramesh is from India. He got his PhD at IIT Delhi, and then he took a number of positions actually around the world, but a lot of them in the United States, first at UCLA, and then Brookhaven, and then he became a research scientist there, and then stayed there until 1994, where he joined as an associate professor at IIT Kanpur. So I should mention that's actually where you see the photo up there. It's actually the Indian Institute of Technology is the basically the premier undergraduate institutions in India, and IIT Kanpur in particular is the one that has the reputation for being strongest in physics. He was there, and I think maybe took a sabbatical at University of Maryland in College Park at the Center for Superconductivity Research. And then in 2009, he left for a 5-year position at the National Physical Laboratory in New Delhi. So this is basically like NIST. It's the equivalent of NIST. Every nation has to have their own standards, and there he helped to build up, in particular, the quantum-based standards that are becoming increasingly important and prevalent worldwide. So then he returned to IIT Kanpur, but has recently moved back to the U.S. and is working at Air Force Research Laboratory. So he's worked in a number of different areas, in magnetism, superconductivity, energy, and today he's going to talk about quantum phases and phase transitions in two-dimensional, highly correlated metals at oxide interfaces. Thank you for having us.
Thanks, Jeremy, for that introduction. I'm really delighted to be here. This is my third visit to this city. The first two were about 20 years ago. For the first one, I came here on a pilgrimage to visit a temple. Second one was for March meeting here, and this one is also a sort of pilgrimage, because now instead of going to a temple of gods, it's a temple of education and great science. So I'm really delighted to be here. What I'm going to talk about today is the work that we have been doing for the last 6-7 years in the area of quantum phases and phase transitions in two-dimensional oxide heterostructures, interfaces, all right? And this work has been done at 3 different places: Indian Institute of Technology, Kanpur. This institute was established in 1960 in collaboration with 9 US universities under the so-called Kanpur US program. So these 9 universities, for 10 years, they helped in building the institute. And this is the National Physical Laboratory in Delhi. Some work was done here. And most of the low temperature measurements below 1.6 K, because at that time we did not have all those dilution facilities, all these experiments were done in collaboration with Jérôme Lessier and others at ESPCI in Paris. Now you would like to know where these places are on the globe. You all know where Paris is. I don't have to tell you that. But I will tell you where the first two places are. So this is the Indian subcontinent here. And I'm magnifying this particular area, northern part, very close to the Himalayas. And that's the view of that area. So these are the Himalayas here. This China beyond this. This is the border between India and Nepal. So this is Nepal here. And if you come about 400 kilometers towards west, you have New Delhi. That's the nation's capital, and that's where the National Physical Laboratory is located. And if you come down about 200 kilometers southeast, you reach the city of Taj Mahal, Agra, which I have shown with a pink heart, because people go there. You don't go there alone. They always go as couples and take their pictures. Okay? And then if you go 200 kilometers towards east is the city of Kanpur. That's where the institute is. Now, let me tell you what is going to be discussed in this lecture. So first I will talk about how transition metal oxide interfaces offer unique opportunity to understand correlated electron physics and quantum phases in 2 dimensions. I will take examples of this well-studied system, lanthanum aluminum oxide, LaO, STO interface. So lots of people are working in this particular area, and this is the reference point, all right? But we have been working not on this particular interface, but a new interface between a Mott insulator and a band insulator. So the Mott insulator is lanthanum titanate, and strontium titanate remains the same. So we are almost loners here. Not many people are addressing this particular interface. So it turns out that because of our loneliness here, our matches with, I'm taking a tennis analog here, our matches with the referees and editors of various journals go all the way up to the 5th set. So we really have to go back and forth many times to get something published. And so I will try to tell you how different this particular interface is with respect to LaO-STO. So I'll talk about 2-dimensional electron gas. I'll provide evidence for that. And then effects of perturbations like optical and electrostatic fields, how the 2D gas response is changed, and 2-dimensional superconductivity and the quantum phase transition. And finally, if there is little time left, I would like to talk about low temperature normal state resistance anomaly. There's a resistance minimum and an explanation for that. All right, so let us start with the transition metal oxides of the perovskite family. We know about, most of us, we know what they are. You have AMO3, M is the 3D transition metal here, and it sits inside this octahedral cage of oxygen ions. So in this octahedral crystal field, the 5-fold degenerate 3D orbital splits into 2 groups of states, T2G and EG. So these are your T2G orbitals, XY, YZ, and ZX. And if we deviate from the cubic symmetry, then these will split further, and they will also split if you bring in spin orbit interaction, the Rashba kind or the atomic spin orbit interaction. So right now we are just considering that these 3 are all degenerate. Now I go ahead and make an interface between 2 different perovskites. So on the top I have one kind, below I have the other kind. And if the interface is very, very clean, you can have direct interaction between these orbitals. So direct exchange interaction between transition metal ions. And that can lead to new magnetic states at the interface. You can also have this interaction mediated by oxygen at the interface. Then that becomes a case of super exchange between two transition metal ions through oxygen. So I'll give you one very good example of this super exchange. If I take strontium manganese oxide, which is an antiferromagnetic insulator, and lanthanum manganese oxide, that is also an antiferromagnetic insulator, but here manganese is in D4 state, here manganese is in D3 state. These two can talk to each other via an transfer of electron via oxygen. And that double exchange, a form of super exchange, makes this interface metallic and also ferromagnetic. So you have a two-dimensional metal which is ferromagnetic. And this was established beautifully by this group at Argonne National Laboratory about 7-8 years ago. You can also produce novel phases in the case of high Tc oxides. So for example, if you take a non-superconducting lanthanum strontium copper oxide, the overdoped regime, and a completely undoped La2CO4, both are non-superconducting, but if you make an interface between the two, very clean interface, there is superconductivity at the interface. So it's another interface phenomenon. One remarkable effect of creating an interface is you break inversion symmetry across it. So because of the broken inversion symmetry, you have a built-in electric field normal to the interface. Now if I consider electrons, diffusive motion of electrons at the interface, then in the frame of reference of this electron, the electric field actually appears as a magnetic field. And the effective magnetic field seen by the electron is momentum dependent, it's written over here. And this electron will have an interaction energy with this effective magnetic field. So that is your Zeeman energy. And I can write down the Hamiltonian in this form, momentum dependent, and that is what is called the Rashba spin orbit interaction Hamiltonian. And I am considering nearly free electrons, so this is linear in momentum. But if the electrons are very close to the nucleus, the wave function gets distorted, and because of that, you can have non-linear terms also here, cubic terms or higher order terms, odd in power. You see similar breaking in similar effects in crystals where there is a lack of inversion symmetry, like woodzites, where the electric field is given as the gradient of the potential, and this is what is called the Dresselhaus spin orbit interaction, but this is different from Rashba, it is coming essentially because of the interface. The other effect of this built-in electric field is the effect on the velocity of the electron because of the Lorentz force experienced because of this field. And that induces a Barry phase. And one can measure the Barry phase by doing perhaps Hall effect measurements. But the simplest way of seeing whether there is spin orbit interaction or not is to look at the transport properties at very low temperatures. And if it is a diffusive 2D electron gas, there will be localization. And spin orbit interaction tries to kill that localization. So we can discuss quantum, the weak localization or so-called quantum diffusion in 2D in this through this simple picture. Let's suppose I have two partial waves of an electron, one going in the clockwise direction, getting scattered elastically at different points, and other partial wave going in the clockwise direction, getting scattered from the same points and arriving back at point O. Since the scattering process is totally elastic, the partial waves do not acquire any additional phase. So these two waves interfere at this point constructively, and the backscattering probability of that electron increases. That's what is essentially weak localization. Now as you increase temperature, instead of having elastic scattering, you will also have inelastic scattering. And inelastic scattering is not a phase conserving process. So you kill weak localization because just by raising the temperature. But if you also have spin-orbit interaction now happening, spin-orbit interaction is strong, then also these partial waves will acquire an additional phase and you will kill the constructive interference. So this phenomenon is called weak anti-localization. So if you see signatures of weak anti-localization in your system, then you can say with confidence that there is Rashba spin-orbit interaction dominating the transport at very low temperatures. All right. Now the Rashba physics has all of a sudden taken the central stage of condensed matter physics. There are a variety of phenomena happening because of the spin-orbit effects. And I have given taken this slide from this very recent review article on spin-orbit interaction physics. So you have all kinds of things like spin Hall effect, you have spin transistors, spin-orbit qubits, spin-orbit torque, chiral magnets, even the Gilosowski-Moria interaction due to spin-orbit interaction and formation of skyrmion-type excitations. And then even in cold atoms, you can see this spin-orbit physics, Dirac metals, and Majorana fermions, and so on and so forth. So lots of exciting things in 2D systems because of the spin-orbit interaction. So now coming to LaO-STO problem. And we all know you have strontium titanate with a band gap of about 3.2 electron volt. You have lanthanum aluminate with a band gap of 5.6 electron volt. And it turns out that the valence band top of STO and LaO, they sort of match, almost perfectly match. And if you create an interface between the two, there will be band bending. And also, lanthanum aluminate is a polar dielectric, so you have these charged layers in this way, whereas strontium titanate is not. And what happens because of the interface potential, you actually, this valence band top of lanthanum aluminate starts tilting in this way. So there is a band bending in this way. And it can happen, you need 1 monolayer, 2 monolayer, 3 monolayer, up to 4 monolayers to bend it so much that it becomes almost equal to or slightly higher than the conduction band of strontium titanate. So you have electron transfer from here into this potential well, which gives rise to 2D electron gas, and there is a hole left behind that is also free to conduct. This is what happens in strontium titanate, lanthanum aluminate strontium titanate interface. Now what happens when I take a Mott insulator? Now again I have shown strontium titanate lanthanum aluminate interface here. This is the band bending and is the transfer of electrons. In the case of lanthanum titanate, if you look at the structure, titanium is in D1 configuration, 1 electron, 1 D electron. And one electron per formula unit or per unit cell, the standard band theory should make it a metal. But it is not, because the on-site Coulomb repulsion is very large. If you bring in 1 more electron and put it at D location, then you have this so-called the Hubbard bands, lower Hubbard and upper Hubbard. The separation is about 5 electron volt. And so the lower Hubbard essentially becomes the conduction band. Now, because of the tilting, you don't have to tilt it too far because this separation is not too large. So even 1 or 2 unit cells of lanthanum titanate on strontium titanate will give you a metallic interface. So that's major difference between the two systems. But again, all the action is at the strontium titanate interface. Now, we have facilities to make such heterostructures. This is the picture that you see here is the facility created at National Physical Laboratory. So you have an excimer laser in the back. It feeds 3 chambers. This one, that's where the oxide interfaces are made. And the laser ablation process is shown over here. So your excimer laser beam hits the target and it ejects the material, creates a plasma plume, and that is deposited on a hot surface over here. You can do reflection, high energy electron diffraction of this surface, and that will give you these spots because you are growing layer by layer. And if you monitor the intensity of one of these plots, one of these dots, then you actually see oscillations, because whenever you complete one layer, you get maximum intensity, and when you start the process of making second layer, the intensity drops. And when again you make a second layer, intensity is at the peak. So from these intensity oscillations, you can actually count how many layers you have put on the surface. So we have created a huge facility. Similar facility exists at IIT Kanpur, but this is a newer one which was made at NPL. So as I told you, the excimer is in the back here. It feeds into 3 chambers. This is the PLD for oxides. This is a combination of PLD and sputtering here. And in the back here is the laser MBE, where we started growing gallium nitride. And there is one more laser in the back. There are more machines. But as I told you, this laser ablation process is highly energetic. Highly energetic in the sense that the material that comes out in the plume can have energies as high as 100 electron volt. And when these high energy ions and atoms hit this delicate surface of strontium titanate, it can create a lot of damage. So it's like the right hand punch of Mike Tyson. So people say that you are doing PLD. There are many known believers, and they say that the material that you create is highly disordered, damaged, and whatever you are seeing, this 2D electron gas, and this is because of oxygen vacancies and this and that. They say you use a gentle process, something like that, very, very gentle. But I must tell you, this is an old picture now. The story had changed, so I should change my picture. But so they say use MBE. MBE is a very gentle process, because when you MBE, anything that you evaporate comes with a fraction of an electron volt energy, and it lands on the surface very gently. So if you can make a 2D electron gas using molecular beam epitaxy, then we'll see that, yes, there is something happening at the interface. Now people have done this. People have shown that even with MBE, you can make nice 2D electron gas at LAO-STO interface. So the bottom line is you only have to know how to do your PLD carefully. So there are lots of tricks involved in that, how to make a good quality sample. All right, this is our very first paper. We started working around 2007 after seeing the very first paper in the area of LTO-STO superlattices, published in 2002 from Bell Labs by Harold Huang and one more person, I think. This 2004 paper, LAO-STO, came in 2004. And here they made a superlattice of LTO-STO, and they showed that using electron microscopy, actually the interfaces are all conducting. And then so we started this, and we made these films on 2 types of substrates. One was 001 strontium titanate, which is isotropic in the plane, and 110, which is anisotropic. 2 directions are not the same. Coordination, atomic coordination is not the same. And what we found was on the isotropic 001 surface, this is 6 nanometer thick LTO, this is 8, 10, all of them are metallic down to the lowest temperature that we could go, about 1.8 Kelvin in our PPMS. On the other hand, if I take 110 surface, if I flow the current in this direction, 1 bar 10, where you have where these are titanium. So these are titanium, titanium, titanium. There is no bridging oxygen here, and this is strontium line. Along this direction, the conductivity actually at low temperature shows an insulating behavior. But on the other hand, if I flow the current in this direction, where I have titanium, oxygen bonds, I see a nice metallic behavior. So this was the first observation of anisotropy in this 2D gas, not LAO-STO, LTO-STO, but LAO-STO also people now have seen this anisotropy, some groups. And you have to be very careful to do this experiment, because if you do a 4-probe measurement, 100 power type, then your all current directions get mixed up. You have to cut the sample a very thin slab along a particular direction, the other one in the other direction, and then measure. All right. So what we have done after that is yes.
So were those gated structures?
This is not gated, it's a straight.
What?
This was not gated.
Okay.
No gating there. This is directly conductivity we are measuring. They are all conducting interfaces. We are not dealing with a material which is not conducting at all. In fact, all of these samples are superconducting also. I am coming to gating now. So this, I don't have to describe this. So we have perturbed the properties of this 2D gas by injecting carriers in a field effect geometry. And this is what the field effect, standard field effect geometry looks like. So you put a dielectric, apply a very large gate voltage here. So you can change the band structure of your channel material or semiconductor in a significant way over a distance lambda, which is called the Thomas Fermi screening length. And this gating was done a lot in the case of LAO-STO, has been done in LAO-STO and in LTO-STO also. This is one way to perturb the electron density in the material. This is a very important tool to change the electronic behavior. The second one was shining light on it. And this is again, we did it for the first time. You shine light on the channel, and it turns out that the moment you open the light shutter, this was a white light source from a quartz halogen lamp, and you see that there is a large drop in conductivity here, resistivity, and it remains conducting. At this point, if you turn off the light, the system tries to come back to its original state, but takes a long time, almost 3 to 4 hours to recover. And this recovery time becomes longer and longer as you go down to lower temperatures. It can take days to come back. But it turns out that its photo response or this photoconductivity is sensitive only to UV light. If I use a helium cadmium laser, which has two lines, 442 nanometers and 325 nanometers, very little change with 442, and this particular UV line 325, which is 10 times weaker compared to this in the laser, you see this large effect. So it's only UV sensitive. All right. So now, that time we had an Indo-French program joint project, so we started sending these samples to Paris, and they put them in their dilution fridge. And it turned out that this LTO-STO interface is actually superconducting. So two different samples were tried, 10 unit cells here and 15 unit cells thick LTO here. In both the cases, a slight minimum in resistance, and then superconductivity at this point, where the resistance is still much lower than the quantum resistance for localization in 2D. It's about 6.5 kilo ohm per square. Now, if we expand this portion, you see very clear signs of robust superconductivity, and also there is well-defined critical current density. So this work was done way back about 5 years ago, and we could infer from this working out the critical field and all that. So it turns out that these are the critical current densities, and the thickness of this 2D gas is roughly about 10 nanometers. The Fermi energy is from 100 to 150 millielectron volt. This is the coherence length from 40 to about 70 nanometers, and this is the Fermi length here, about 10 nanometers. Now we've again the French group and our interactions with them, we started studying the effect of gating on the transition temperature. So let us start with a sample whose behavior at 0 gate voltage is somewhere here. You barely see sign of superconductivity around 100 millikelvin. You apply gate voltage, make it more and more positive, the TC goes up and then comes down. So there is just some sort of a dome structure if I plot TC as a function of gate voltage. On the negative side, you drive the superconductivity out, and you end up with a sort of a dirty metal whose sheet resistance in this limit of temperature is still lower than the quantum resistance per localization is 2D. That's why I'm calling it a dirty diffusive metal. And it turns out that the behavior of the sheet resistance as a function of gate voltage is actually not monotonic. Positive side, the sheet resistance changes pretty fast, and the negative side is almost like a plateau. So all the information that I have from these two insets can be drawn in this colorful picture, where you have the gate voltage, you have the temperature, and the color code here actually tells you the sheet resistance. When the sheet resistance is very, very small, you have superconductivity and metal here. When the sheet resistance is somewhere around up to this 2.5 beyond kilo ohm square, it's not actually an insulator, it's like a dirty metal over here. So the question was, why this kind of a dependence on gate voltage? Why is it not linear, for example, the sheet resistance as a function of gate voltage? So the next experiment that was done is a very important experiment, and it was done using the high magnetic field facility at Toulouse in France, so measuring Hall effect up to about 45 Tesla as a function of gate voltage. So when you have negative gate voltage of about minus 200 volts, there the sample is almost superconductivity is all gone. And you see that the Hall resistance is perfectly linear in field all over the entire range. And you increase the gate voltage now, come to 0, it remains linear, and when I go to 100 and 200 volts positive, you start seeing the signs of nonlinearity here. We have data now much closer steps in this range up to 10 Tesla, and this is exactly reproducible, the nonlinear behavior, and there is no hysteresis. So I cannot say that it is some sort of an anomalous Hall effect and there is hidden magnetic order in the system. We don't have any evidence for magnetic order in these samples.
So hysteresis and anomalous Hall effect are not necessarily
Not usually in ferromagnets, if you measure the anomalous Hall, there will be hysteresis.
Yeah, but there can be other origins of anomalous Hall effect.
Yes, sure. Yeah. So, but if it is related to magnetism, then I would expect at least some irreversibility.
Well, unless there are two types of magnetism.
Okay, all right. So now in order to explain this nonlinear field dependence, we simply went ahead and used a two-band model. Assuming that the total sheet resistance comes from this formula, where you have one type of carriers with carrier density N1 corresponding mobility mu1, and the second one is N2 and mobility mu2. And after this analysis, what you get is, if I plot the mobility of the mu1 and mu2 type, so mu1's, the mobility is very small, and mu2, mobility actually is at least higher by a factor of 100 or 200. So we have high mobility carriers, these ones, where is here, right here, this one, and low mobility carriers here. And what are the corresponding carrier concentrations? So when the gate voltage is all negative, most of the carriers are the low mobility carriers, which are this green triangle here, goes down here. there are no high mobility carriers at the negative gate voltage, almost 0. But as you go towards the higher positive gate voltage, the number of high mobility carriers actually goes up, this N2, and this starts coming down.
So both your M1 and M2 increases, but Y and pole decrease when you increase the backing further, right? The purple curve.
Purple curve is the total Hall.
Right, so shouldn't that increase because both M1 and M2 increases?
This is coming down, and you are using, in fact, because of the mobilities, you cannot directly translate the two. You cannot directly add the two. Okay, the mobility factor also comes in. So now, if I look at if I add by N1 and N2, that is my total is here, the round circles. Okay, the N1 and N2 that I get from my two-band model, if I add the two, this is my curve, and it turns out that it matches exactly the carrier density that I get essentially by using the charging formula for a capacitor. Okay, so this is the charge I am putting in at the interface, and that adds up to N1 plus N2. Okay, so now. So the question is, where are these high mobility carriers and where are these low mobility carriers? So we have to look at the electronic structure of the interface. And if I look at the electronic structure of the interface, so these are titanium 2Tg bands, dxy, which is isotropic in the xy plane, and dyz and dzx. I have not put in any spin orbit interaction here. This is essentially because of the confinement along the z-axis and also slight distortion from the cubic symmetry. So that's why you are getting this splitting of these three bands. And so these are the effective masses. Band theorists have worked out. This is isotropic, and the band mass is something like this. And these are extended. They extend deep into strontium titanate, YZ and ZX. And the band mass here is higher, about 3.13 mass of electron. Okay. Now, what happens at the interface? The interface, this is your triangular quantum well, and these you start filling it. So first is this guy. So these are confined levels of this dxy in the quantum well. If I Fermi energy is somewhere here, then the extended view of this is here. So first you will fill the dxy, and then you start filling yz and zx. And it turns out that these guys are the so-called low mobility carriers. They are large number, and these are the electrons which fall in yz and zx. These are the so-called high energy, high mobility carriers, but their number is small. That is our interpretation. So our interpretation is that.
Sorry, why would the low mass band have low mobility and the high mass band have high mobility?
Yeah, that is a little contradiction there. It turns out that these guys these two bands can extend deep into strontium titanate, and they take there the advantage of high dielectric constant of strontium titanate. So that makes the mobility is larger. And so the final consequence of is this as our summary. So we have two carrier model. So we think that superconductivity is in the light carrier band, high mobility band, and the magnetism is coming from here. And if at all there is magnetism, in our case the only evidence of magnetism is the Kondo scattering coming from these localized moments which are confined at dxy. All right, so now we look at the superconductor normal state or superconductor insulator phase transition in this system in the limit of t is equal to 0, 0 temperature quantum phase or the quantum phase transition. Now, if we look at the superconducting state, we have the order parameter. The complex order parameter has two parts. One is amplitude and a phase. Amplitude is equal to the square root of the condensate density, and the gradient of the phase gives us the kinetic energy of the superfluid. Now we can destroy superconductivity in two ways. Either we can destroy the amplitude, basically the pairs, cause depairing, or we keep this intact, only break the phase. So their pairs are there, but they are not phase correlated. That will lead to this, the macroscopic quantum state will be destroyed either by playing with this guy, or by playing with this, or playing with both. But what are the energy scales involved? If I take a bulk superconductor like niobium, the order parameter is in the BCS limit is 3.5 k beta Tc. So this turns out to be the easiest way to destroy the superconductivity in bulk samples. You do depairing of the pairs. And the energy associated with the phase is given by this expression half T gradient of phi squared. This is like this twisting of a spring, the energy stored in a spring. And and this is equal to, comes in terms of the number density of Cooper pairs, the mass and the velocity squared of the superfluid. In bulk superconductors, phase is very robust. You cannot play with the phase, you can only play mostly with the order amplitude. And that's the way of destroying the superconductivity. But now, if I look at the bulk material like niobium once again, so this is my superconducting transition, and we know about fluctuation effects. So even before I reach Tc, there is action in this temperature range. That's the so-called the fluctuating regime, where you have electrons talking to each other, pairing over a length scale xi, or you can say that you have these superconducting puddles forming somewhere here. And the length of these, or the size of this interaction, the correlation length, diverges as you approach the Tc, becomes of the size of the sample. So the whole sample becomes then sort of covered by these puddles, and whole sample becomes superconducting. And these puddles are also fluctuating in time. They come, go, come, go, come, go. And what is the time scale associated with that? That is given by this time tau, which goes as xi to the power z, and z is roughly 2. So as you can say that as this diverges, I go here, tau also becomes infinity. So the fluctuations live forever, and that's why you have a transition. So everything is driven by temperature. Now if I push the temperature down, in 2D there are more complications, so let's not talk about that. But if I go down to the lowest temperature, then there are no thermal fluctuations. What drives the transition? So these all happen because of the quantum fluctuations in the system. And we can again write down this correlation length, which goes as delta to the power minus nu, and delta is actually the distance delta is actually what you are doing is you are playing with the Hamiltonian, one of the parameters of the Hamiltonian, varying that, and that causes the transition. So that could be carrier density, that could be magnetic field, that could be pressure, that could be strain, that could be disorder. There are many things. So this delta is actually, if I look at a carrier concentration driven transition, then I can write delta as n minus nc. This is the critical concentration required. Similarly, the critical field, critical disorder. So you will have a quantum critical point here at which at t is equal to 0. If you cross this line, you go superconducting. Here you are normal. But we can never reach 0 temperature. We have to study it at a non-zero temperature, and non-zero temperature becomes high, then thermal fluctuations also become important. So the competition between the thermal fluctuations and quantum fluctuations is decided by this ratio. So above a certain temperature, the quantum fluctuations become irrelevant actually.
So delta is the disorder of amplitude.
Excuse me?
What is the delta here?
This delta?
The capital delta.
Oh, this one?
Is the order parameter amplitude or the disorder?
This is disorder. It's a critical disorder, yeah.
So this is the assumption that those transitions with respect to this
Excuse me?
So it's like you assume the phase transition with respect to this parameters are all continuous as opposed to not.
I'm taking a continuous phase transition. Yes, yes, not first order.
That's an assumption.
Yeah, that's an assumption. Yeah. Well, superconducting transition is a second order
No,
transition.
the second order is with respect to time.
Hmm.
You know, it depends on what kind of parameters you're talking about, right? So it's not a proof. It's second order for all parameters.
Yeah. But here I'm considering only a continuous phase transition. Hmm?
Temperature is second order, right?
Hmm.
You just say the parameters, you take the derivative.
Yeah, yeah, okay,
But
okay.
then you have other parameters. That
Yes,
are
yes. Okay. So now I can sort of write the behavior of the resistivity very in the critical regime by using the scaling argument. So where you write this is your the parameter that you are changing, k minus k critical, which could be the field, could be disorder, or could be carrier concentration. And then in the denominator you get temperature and these two exponents. Now the fundamental question to ask here is, once the superconductivity, if the system is stripped off of superconductivity, what is left behind? The answer is, when the phase is destroyed and the disorder is sufficiently strong, that means the sheet resistance is more than the quantum, 6.5 kilo ohm square, we have the so-called localized boson. So that's what is called the dirty boson picture of a superconductor insulator phase transition. If the disorder is weak, then we have this tantalizing possibility of having a bosonic metal. But it is still not established that there is indeed a bosonic metal in these systems. And then when pair breaking is dominant, you will have fermions, and if the resistance is more than this, then you have sort of a localized fermionic system. And if the resistance is less than this, then you can say a weakly localized two-dimensional conductor. So there are many possibilities depending on whether you are playing with the phase or you are playing with the amplitude. So this is the field-driven superconductor normal transition in LTO-STO. Field is applied perpendicular to the plane of the 2D electron gas, and you see here sheet resistance as a function of temperature at different values of magnetic field going up like that. And you see the conductance here, the variation, conductance goes up as I increase the gate voltage, and this is the transition temperature goes up as I increase the gate voltage. Now if I expand this portion somewhere here, it turns out that I have a critical value of the magnetic field at which the sheet resistance actually becomes independent of temperature. So that's an indication of a continuous quantum phase transition. So I can define this resistance at which this happens as, where is that parameter here, Rx, which is roughly about 372 ohm squared. And the corresponding field at which this happens is this much. But if I continue expanding this portion up down here, I come to another region where again the resistance is reasonably constant in temperature over this range, somewhere down to about from 20 millikelvin to something like here, about how much would that be, 80 millikelvin or so in this range. So this critical resistance Rc corresponding to this point is here, and the critical field is here. But we must remember that these values are much smaller than the quantum resistance for localization in 2D. Now we can do a scaling analysis of these data. So this is the standard scaling ansals. So what you do is, if I plot my sheet resistance as a function of magnetic field at different isotherms, temperature is constant. So it turns out that all of them cross through this critical field Bx. And this is the normal site, this is the superconducting site. And I can do a data collapse for this as well as this. So, this is the superconducting side and this is the above transition. And I can do a plot of log of t versus log of this small t, and it gives me the exponents z nu, and this gives me the critical field Bx. So, this is what happens at the first transitions happening at a slightly higher temperature. And at very low temperature, the second thing, again you can do a data collapse. Everything looks similar except the exponents are very different. Here it is 0.66 and here it is 1.5. And the explanation for that is we are going from so-called clean limit to a dirty limit. And why that happens, that two carrier model becomes very important here to explain this. So, the picture that we have presented is this. We have a sort of phase correlation length L sub phi, or the dephasing length, which goes as T over 1 over Z. And so, it diverges as I go to lower and lower temperatures. The other length scale in the system is L sub D. L sub D. So, what we have is these low mobility carriers are actually forming this uniform background of electrons, the yellow one. And the high mobility carriers, whose number is very small, are undergoing condensation, making superconducting droplets. These. The size of the droplet is L sub d, and it turns out that here the phase correlation length is actually smaller than the size of the droplet. Phase correlation length is the length over which the Cooper pairs are represented by a spin here. So, all the spins are lined up in the same direction, they are all talking to each other. All the action is inside one puddle. But now, when this becomes very large, L sub phi actually covers many droplets. So, now one droplet is talking to the other droplet. So, here there is a regime change from here to here, and that is what probably leads to these two exponents. Now, that was a superconductor normal metal transition driven by a magnetic field. The tuning parameter is magnetic field. Now, what we are going to do is do the same thing. The tuning parameter is the carrier concentration. So, the carrier concentration, so carrier density dependent zero field transition in the limit of zero temperature. These data are for LTO, STO, and you are starting at plus 20 volts. So, there is a transition here, this is superconducting, and as you go towards negative voltage, somewhere here you see that your seat resistance is actually independent of temperature, and above this voltage you start entering the regime of a dirty metal. So, again we define a critical value of gate voltage, or in other words a critical carrier concentration that at which we enter the superconducting phase. One can do a scaling analysis of this also. So, this is the superconducting part, the positive gate voltage, this is the non-superconducting part, and this is the universal crossing point BGC happening at this point. So, you can collapse the data. It is a nice collapse for the below the transition, the gate voltage below which we have superconducting state, and this is the gate voltage above which we have a negative side of the gate voltage where we have non-superconducting state. And you look at the exponent G nu, it is 1.6, which we got again in the earlier magnetic field driven transition at very low temperatures. Now, how different is this from the LAO-STO interface? There also you have superconductivity, and it turns out that there is hardly any difference between the two systems. Actually, we have done a very careful study of careful comparison between LTO-STO and LAO-STO. We see similar signatures in photoconductivity. We see similar signatures in the Hall effect and other things. So, in my opinion, these two materials are not actually very different. All the action is in the strontium titanate, just below whatever you put on the top. And again here you can see exactly the same thing, same exponent. So this is the carrier concentration driven phase transition. And I can plot a diagram here. So it's a quantum critical point in carrier concentration versus gate field phase space. So this is my 0 gate voltage. I'm making it more and more negative in this side. And here I have all low mobility carriers, very small concentration, but they are all homogeneous. As I make my gate voltage less negative, I enter this point at which now I start seeing the phase separation. So if I go up, I get the low mobility carriers follow this path and the high mobility carriers follow this path. So I get a mixture where I have low mobility carriers and high mobility carriers. So a two-phase, a phase separated regime where I have superconductivity. So this is the picture that we have proposed for the superconducting transition in these systems, happening essentially because you have two types of carriers and the condensate is only in one type. Condensation is taking place only for one type of carriers. Now the question now, the second, this is a very recent measurement done again by the French group, and this is a measurement of the phase stiffness. And this is a little difficult experiment. It was done using microwave reflection experiments. So we had a coplanar waveguide on which you mount your strontium titanate lanthanum aluminate sample, and then you also have surface mounted components, capacitors and resistors and inductors. So we make an LCR resonant circuit, and you drive microwaves in and look at the reflected microwaves using a vector network analyzer, a VNA, basically looking at S21 parameter.
At what frequency?
Oh, this is somewhere about 10 gigahertz or so. I'll show you that data. And so you can see this is what we are measuring, the reflection coefficient, which is out, the total power out divided by power in. And this is related to the complex conductance of the circuit, which has a real part. And when the superconductivity sets in, this is my 2D layer, this is the capacitor coming because of strontium titanate, and I get an imaginary part, which is essentially coming from the response of the superfluid. And how do I write it down? This is related to the kinetic inductance of the superfluid, Lk. And so I can write down my phase stiffness. The experimental value of phase stiffness is basically these constants 1 over the kinetic inductance, which I am measuring from here. And then I can rewrite this expression, and that gives me the number density of the superconducting pairs in terms of the phase stiffness. So I can deduce this quantity once I know this. I can also write the phase stiffness using the BCS expression in the limit of 0 temperature. The BCS theory gives us the phase stiffness equal to this 1 over normal state resistance and the gap parameter at t is equal to 0. So what do we see? All right, this is the response of the circuit in the normal state at roughly about 450 millikelvin. So you are looking at this is the phase and this is your resonance of the circuit, somewhere around, this frequency is much lower, it's about, you can see about 2.3 gigahertz. So this is happening in the normal state. Now I go down in the superconducting state. This is at a positive gate voltage of 14 volts, and this is the behavior of the sheet resistance. So you have a superconducting transition somewhere around 200 millikelvin, and this is the response of the microwave circuit. So you start seeing this kind of a behavior here. This is the behavior of this is frequency and this is sheet resistance. Yes. So resonance is actually shifting, and here at a slightly higher gate voltage plus 50 volts, the transition is much more robust here. All right, so what can I infer from this? So first thing I do is, this is my superconducting transition temperature as a function of gate voltage. I have the so-called dome here a little bit. So I call this an underdoped regime. This is overdoped regime, and then eventually if I make the gate voltage much higher, it comes down to 0, Tc. And what is this quantity here? This is the phase stiffness calculated using the BCS formula. So it rises and follows this kind of a behavior. And what is the dependence of the phase stiffness that I get from my experimental data? That is over here. And so clearly in the underdoped regime, it does not follow the predictions of the BCS theory. All right. I can go a step further and calculate the gap parameter. So what do I do to calculate the gap parameter? So this is my experimental gap parameter. It's coming from, I'm using this formula. Phase stiffness is related to the gap parameter. So this is the gap parameter calculated using the BCS theory. Gap is equal to 3.5 k beta Tc. This is the behavior of the gap. On the other hand, if I calculate the gap using this formula for the phase stiffness, the gap parameter comes out like this. So there is a clear difference here. Below here they merge together. And there is a very recent tunneling data on this measurement of superconducting gap. It turns out that at the optimal doping, the value is roughly about 40 microelectron volt. And this is comparable, it's slightly lower, it's about something like 22, 23 microvolts from our measurement. But the tunneling measurements in this regime actually show a much higher gap. And here we are measuring it much lower. Now the reason for that I think is because this is the gap which is actually we are looking at the response of the condensate, looking at the phase stiffness. And if you look at the tunneling gap, it is basically coming from the single particle density of states. It does not mean that you have actually condensate there. You may have pairs, but there won't be any condensate. So the hypothesis then is, in this regime somewhere, you may have these so-called preformed pairs, which we also talk about in high Tc superconductors, but the fully phase full superconductivity appears only in this regime. And here you can say that it is almost like the weakly coupled Josephson junctions. So that is the recent story on this. And so we can also calculate the number density. So to calculate the number density of the electrons which are participating or which are making the carriers, superconducting carriers, from this formula. This is related to your phase stiffness, and we have measured phase stiffness experimentally. And it turns out that this number density of carriers which are contributing to superconductivity at the highest Tc is only 2 into 10 raised to the power 12 per centimeter square. The measured carrier density from Hall is much higher than this. So what we are saying is only 2 to 3% of the total carriers are actually contributing to superconductivity. Rest they are all forming the so-called low mobility background. So this is the data. Whatever I am plotting here. So this is the number density of high mobility carriers that I got from the two-band analysis. This follows this path. And the number density of carriers that I am getting from this analysis is somewhere here. They are reasonably close to each other. But what I am saying is their number, if I compare them with the total number of carriers, they are only 2 to 3%. This is the current picture for superconductivity. So how much time have I taken? An hour. So I can conclude at this stage. And although I have some slides on the normal state transport, I can skip that and conclude. If you want to sit here and listen to that also, I'm ready, but already 1 hour is gone. So let me conclude. All right. So what we have is a two-dimensional electron gas is seen at the interface of LTO-STO, and it appears to be same as the gas we see at the interface of LAO-STO. I mean, as far as all the measurements that we have done. So what we conclude is then it is simply actually the physics of titanium D0 and D1. And all the action is happening at the interface in strontium titanate. When you transfer electrons from the top, you are creating, some of them are in strontium titanate, all of them are in D0. Once you transfer electrons, some of them go in D1. So you have D0, D1, and that is giving you the conducting layer, and that's where all the action is. And the width of the superconducting layer is something about 10 nanometers. And these are actually candidate systems to study superconductor insulator quantum, or superconductor insulator, or superconducting metal, normal metal quantum phase transition. The transition has been driven both by field tuning as well as carrier concentration tuning. And an electronic phase separation is seen in the system as a function of doping, which has its signatures in the nature of the quantum phase transition. These are very good systems to study quantum phase transition in 2D, because the earlier people used to make thin films, and they would vary the disorder by changing the film thickness. So every sample is different. Here you have one sample, and you are changing the carrier concentration by simply applying the gate. So it's a much better system that way. Superconducting phase stiffness measurements suggest that destruction of phase coherence is responsible for the superconducting transition. That's the latest microwave data in the low doping regime. So low doping regime, you have the possibility of these pairs, uncorrelated Cooper pairs, existing above the transition. And when you have a robust phase coherence, then only you see bulk superconductivity in the underdoped regime. Overdoped regime, everything is normal. So this phase transition in the underdoped regime is akin to that of absorption junctions connected by a metallic two-dimensional gas. Finally, a very small fraction of carriers, carriers, 2 to 3%, actually condense to give the superconducting phase. So this is the conclusion of all these experiments. And I don't know what we are going to do next. We want to look at this anisotropy a little more, but this experiment has to be designed in a proper way, because you cannot use very large samples. It has to be a very thin channel. So with that, let me thank all of you for listening to me. There are many other things here, so I'll just finally thank my collaborators who have worked for this. This is very important, the measurement of thermoelectric power, and we see signatures of Kondo here. All right. Okay, so lots of people have contributed to this. The work actually started at IIT Kanpur somewhere around 2006, 2007. And then when I moved to NPL, we started action at NPL, created the facility and started measuring them. We also got a dilution fridge. Unfortunately, when the dilution fridge started working, I left NPL, so I hope they are making good use of it. And a lot of work actually was done by these people. It's mostly their work actually. Nicola and Jerome. Gyanendra is my student. He graduated from IIT Kanpur, and then he shifted to Jerome's group. He has been there for 5 years now, doing all kinds of measurements. And the theory contribution is from Marco Grilli in Rome. And there are a lot of electron microscopy was done, which that I did not show here, and that is Ime Zhu from Brookhaven. He did very nice lattice imaging and electron energy loss spectroscopy and all that to look at the chemical state of these ions at the interface or across the interface. So his input was very important. And finally, lots of funding agencies. And this program was very important. Indo-US that I had with EMA, and Indo-French that I had with Jerome. That's what led to this international collaboration. Yeah. Thank you.
Okay, so any questions from the audience?
So due to the monotonous of lengthen tightenate,
Excuse me.
due to the monotonous, the Mott insulator
Oh, okay.
nature of lengthen
lengthen
tightenate,
tightenate.
lengthen tightenate. So do you expect anything special for the superconductivity in LTO, STO, which is yet to be seen compared to the LSTO interface?
I'm not really sure if the Mott insulator is doing anything to this. The only thing is in LTO, STO, the top layer is supposed to be insulating. Because if you look at the transfer of electrons is happening from the lower Hubbard band, not like LAO where you are transferring electrons from the conduction band, or sorry, the valence band. So you leave a hole behind. And here, the moment you create a hole in the lower Hubbard band, there is a charge transfer taking place, which makes the top layer actually insulating. There's a nice paper by Mohit Randheria, and this will recently came out. So that is one difference between these two systems. Other, I don't know. Magnetism may show something, but these titanium D1 in LTO, it is an antiferromagnet. But doesn't seem to affect the superconductivity. Superconductivity looks exactly the same. Because this French group, earlier they were getting their LAO, STO samples from somewhere else. But then we started making samples at NPL, and they like our samples more. So it turns out that the LAO, STO is also superconductivity is exactly the same. So that's why I feel that all the action is happening on the strontium titanate surface, and the dielectric constant of strontium titanate is playing a very important role because it just blows up as you go down.
But it's field dependent. It decays very fast as you increase the electric field.
Oh, yeah, okay, yeah. So, I mean, the microwave measurement actually in the beginning became very difficult because strontium titanate dielectric constant is very high. So,
I have a question. It is very interesting, this microwave measurements showing with the interpretation of the Josephson, Jepson.
Yeah.
So the question is, well, okay, so you didn't mention anywhere in your talk anything about, ferroelastic domains and what happens at low density, and there's a lot of work on, LAO, STO, which you just said is very similar to LTO, STO, showing that the transport is very anisotropic and, even dominated by filamentary transport. And so how does that affect your interpretation? I mean, I think it's consistent with the idea of Josephson couple junctions. I mean, those could be the network of.
See, that's why we would like more people to look at LTO, STO, this ferroelastic domains and all that. Everybody, the base system is LAO, STO.
The base system is STO.
But top
I mean,
is
all of the domains are coming from STO.
STO, right? But the system is, everybody has taken the LAO, STO system to study.
Yeah, that's true.
So
actually, it's true that LTO, STO, near the surface, the nucleation may be different because a lot, changes in lattice content
It's
and
possible.
so forth.
It's possible. Yeah.
It's possible that there would be some subtle
and
differences.
LTO is a slightly difficult material to handle because if you put a little bit of extra oxygen in LTO, it becomes a metal, right? It has this propensity to lose one electron. Titanium D likes to lose one electron and get some oxygen. And once you oxygen dope it, it becomes a metal. And if you put too much oxygen, it goes into a pyrochlore phase, which is insulating. So that's why making these LTO, STO samples, good samples, is little non-trivial. People have written that, this all your LTO is all metallic.
Those are probably people who didn't make it right, right?
Yeah, so some people say that it's all metallic, so that's why they don't want to touch LTO, STOs. I think we think it's a good metal, interesting metal. I wish more people were studying it. I think the Stanford group, Yuri Suzuki, I think they have started doing something in this
Yeah.
area. Yeah,
That's right.
yeah, and yeah.
Okay, well, let's thank Ramesh again.
Thank you.